All right, so we'll get started. So thanks, guys, for first showing up to our session. My name is Avinash, and I'll let my co-hosts introduce themselves.
Hey guys, I'm Alex.
Hi, everybody. I'm Vineet.
So we're pretty excited to welcome you to our new initiative for Emory School of Medicine, which is a series of machine learning workshops. So this is the first workshop in that series. And as you can see, it's going to be an introduction to the field overall. So I guess first, in terms of a flow for how the workshop is going to go today, I'm going to start first by talking about kind of a high level and conceptual overview of what machine learning actually is. And then I'll cover some of the basic terminology in the language of machine learning as well, which will be helpful for you as you move forward in projects or read papers and so on. After that intro, Vineet is going to be diving right into a series of interactive notebooks, which is where you're going to get to see how machine learning is actually implemented in projects. And then lastly, Alex is going to be talking about some medical use cases for machine learning today. So let's start first by kind of diving right into what machine learning actually is. So it's a fancy sounding phrase, but what it really boils down to is finding complex patterns within data using math and stats techniques and on computers, right? So you might wonder, what's all the hype about if this is just math, right? And the power lies in machine learning and its application to problems that you care about, right? And that's what we're going to be showing you through our examples. So first, let's kind of frame where machine learning falls within some of these other categories and buzzwords that you may have heard about, right? And so this is going to help as you think about papers, think about new products that you review, and it kind of helps clarify some of this confusing terminology that people kind of use interchangeably quite a bit, but are actually different things. So machine learning is really about finding just the raw patterns within data. Within a kind of subset of the category, there's neural nets and deep learning, which you may have also heard about, but they're kind of not synonymous with machine learning overall, right? So neural nets are a kind of more complicated technique that we're not going to be covering in these intro notebooks, but what we're going to rather be focusing on is what's in the gray, which is the kind of classical machine learning techniques, or the more simple ones that most of you will probably be able to get started with. Kind of outside of the scope of machine learning, or I guess in a slightly larger category, is artificial intelligence, which is where you take the patterns that you learn in machine learning, right? And then you apply those patterns to be able to make decisions and take actions from there. So what we're going to be covering is just kind of a very small portion of machine learning, and it's kind of called classical machine learning. So let's start first with a medical example, and this is something that probably all of you guys have seen, well, most likely have seen many times. It's a set of lab results, right? So imagine that you have a patient whose name is John. They come into your office for their annual checkup. And before you get to do a history, take a history, or do an exam, John hands you a printout from an outside lab and asks you to interpret these lab results, right? John wants to know, do these lab results look healthy or not healthy? So it's a bit of an oversimplification, but let's take a couple of seconds and go ahead and kind of look at these labs and think about it in your head and try and interpret whether these look normal or not. So now that you had a couple of seconds to think about it, what you will see is that these are, as a whole, normal lab results, right? And so what we as humans just did was we classified something, right? We looked at data and then we tried to classify whether that was healthy or not healthy. And that's what machine learning tries to do, right? It's exactly the process that you just did in your head. And we as human beings are pretty good at it, especially right now. But machine learning, the goal is to be able to do the same thing, and its power actually lies in its ability to go further and look at data that's at scales that is hard for us as humans to comprehend, and then to understand patterns within that data. So why should you as a medical student care about machine learning? And this is a topic that Alex, Vinit, and I had discussed a lot initially, and this is really the reason that we created this workshop. First, it's that honestly, anyone can learn machine learning, right? At least at a conceptual level, even if you don't think about the math, the concepts are kind of accessible to anyone. Second, machine learning is already becoming an important part of medicine, and Alex will be giving you some specific real-world case studies for this towards the end of the presentation. But most importantly, machine learning is a tool that's going to help you treat your patients better, right? And that's why we think that this is something that all medical students and all physicians should know about. So let's shift gears a little bit, and before we jump into kind of the main concepts and the terminology, let's think about an example that illustrates the concept of inference, which really kind of underlies all of machine learning. So in this image, go ahead and start by looking at the shadows, right? You see a rectangle, you see a circle, and as you might imagine, the goal is to figure out what the object in the middle looks like. But the caveat is you want to do so by only looking at the shadows. So the shadows are basically like the data that you have, and the object in the middle is analogous to what we're trying to study, right? So inference is the process of trying to shine the lights from different angles during the process of trying to build up an understanding that this object in the middle is actually a cylinder. But to do so by only looking at that data, which is the shadows that you have. So let's frame the concept in a slightly different way that you might be more familiar with. So in medicine, when we interview patients, when we generate a differential, when we look at labs, when we look at imaging, basically anything that we do, we're working with data, right? And the data comes in different forms. It could be words, it could be numbers, if we're talking about lab results and so on. But why do we care about this data, right? And at a high level, it's because we're trying to do something to help our patients be healthier. But at a lower level, that process requires that we need to identify patterns within the data that we have. And so this is one of the types of patterns that you see, right? It's modeled by something called a linear regression, which we'll be going into later on in the session. But what's really cool is once we can identify a pattern such as this line, right, we can start to do things like make predictions about the health of our patients. And that's kind of the power of machine learning, right? It's especially powerful at scales, beyond the couple of dots that you see on this image, where for even us as human beings, it's hard to understand, but using math, you can start to identify patterns in the data. So when you're doing research, you got to first figure out what type of problem you're trying to solve, right? And so there are a couple of major categories of problems that you can tackle using machine learning. So the terminology that you see on this screen is pretty important because it's standardized across the field. So these are the terms that you might see when you read a paper about machine learning. The first category that we're going to cover is called classification. And this type of problem is one where you need to basically pick a category that an object belongs to. And a medical scenario of this is let's say you have to pick a diagnosis for your patient. If you have a patient with a cough, your differential might include like pneumonia, asthma, COPD, and you want to identify which of those disease categories corresponds to our patient's diagnosis. That's a classification task. The second kind of major category that or type of problem that you may come across is a regression problem. And so here we don't care about numbers, but instead we want to predict a continuous variable, or we want to predict a number. So in a medical example, this would be, can we predict the actual A1C value for a given patient? right? Um, and so this is a regression task. The third category that you see, which is clustering, we'll cover briefly later, but it's a little bit more advanced, so we're not going to get too into it at this point. We're also going to talk about different types of learning, right? Because we've talked about types of problems, but how does a machine actually learn? So the first and probably most common type is also known as supervised learning. And so to understand this, take a look at the figure and imagine that it's a set of patients. You can start off by imagining that each dot is a patient and that some of the dots are red and some are white. Let's assume that the red dots correspond to a diabetic patient and the white dots correspond to a non-diabetic patient. And in supervised learning, you as the PI or as the study leader, you're going to explicitly define, aka you're going to label which patients in your data set have diabetes. So that's what we've done here, right? We've taken this data and we've manually, or as humans, we've manually labeled this data with the ones corresponding to diabetes for that given patient and the 0 corresponding to a diagnosis of no diabetes for that patient. And in addition to just that diagnosis, each of these patients also has a whole suite of other variables, information like their A1C, their age, their waist circumference, BMI, and so on, that we've also stored, and we're going to be feeding that into the model, right? So when we do that, when we provide this data and the label to our algorithm, it, using some fancy math that's kind of hidden so you as the end user don't have to worry about it, it learns the relationship between all those variables. It learns the relationship between BMI and presence or absence of diabetes, for example. Now that we've learned the relationship, or that our model has learned the relationship, this is where it gets interesting. Let's say you have a new patient who's from a completely different population, a different city, compared to our original data set. So we don't know whether this patient has diabetes or not, but we want to figure that out. And instead, the information that we do have for this patient is kind of their raw lab values, their imaging, other information. We just don't have a diagnosis. So when we feed this new data point into the machine learning model that we've already built, our model makes a prediction on whether our new patient has diabetes or not. In reality, the algorithm just predicts a 1 or 0 because that's the label that we've provided to it. But then we as humans will interpret that 1 as diabetes because that was our definition. And this is kind of the crux of supervised learning, right? You're using labeled or defined data to learn a pattern, and then you apply the model to make predictions on new data that you've never seen before. And the really, really powerful thing, in case it's not clear already, is that unlike traditional programming or traditional studies where perhaps you're explicitly defining in your code that you're going to say that a patient has diabetes if their A1C is above 6.5, for example, we're not explicitly defining the relationship in machine learning. Our model learns that relationship by itself. And once again, it does that using some math like linear algebra that happens behind the scenes so that we don't need to think about it if we're going to apply machine learning. The second major category is unsupervised learning. And so here, this is called unsupervised because unlike in the previous example, there's no labels here like diabetes or no diabetes. And so let's say we have a completely new group of patients. We don't know any of their diagnoses. Once again, all we have is their raw data, their physiological measurements. In this case, keep in mind that we're going to assume that there's some inherent differences between some of the data points. So we're going to assume that there are actually 2 or more different categories of patients here, but we don't know what rules separate these categories. So clustering is one of these unsupervised learning techniques where what it does is it basically just groups data that has similarities into the same cluster. And then it separates that data from groups with different qualities. And the way it separates it is it does math to create this line. It could be a line, it could be nonlinear. It's also known as the decision boundary. But the main point is it learns, what rule separates these two groups. And once again, remember, this is completely unlabeled data. And so it's just basically the model says, we think there's actually just two populations here, even though it doesn't know that it's a population of diabetics or non-diabetics. Another kind of real world example of this might be, let's say you had a collection of Netflix movies, but somehow, the genre labels got deleted. So clustering is a technique that you could use to automatically predict which movies might be similar to each other. And so therefore indirectly may belong to the same genre. So let's briefly kind of review what we've discussed before moving into our demos. We've talked about types of problems, which are classification and regression tasks. And we've also talked about types of learning, right, which is supervised and unsupervised. So, we know this is kind of complex terminology and probably is mostly new to most of you. So we wanted to, before jumping into the demos, kind of come back to this slide to remind you that at its core, machine learning is really just about finding patterns within data, right? So keep that in mind as we jump to the next session or to the next portion of the workshop. So I'm going to hand off to Vineet, who's going to be diving into some interactive examples.
Great, thanks, Avinash. Could you go to the next slide? So our next little bit is we're gonna dive a little bit into the notebooks, but before we dive into the notebooks, I did want to, we wanted to talk a little bit about what our goals with MedML is, what our goals are. So big picture, the goal of MedML is to explore basic concepts in machine learning in the context or framework of medicine. What do we all share in our training? We share the medical language, we share the medical knowledge that we have. So if we can anchor our learning of machine learning into the medical environment, it should help us, learn machine learning in a little bit more focused, accessible way. That's a primary goal. Our goal is to connect medical students to the rich resources that are already out there. There are a lot of fantastic machine learning resources out there already. Our goal is not to remake those in whatever medical language. Our goal is to get medical students at Emory up to a point where they can easily and confidently access those resources. So I want to stress that a lot, because what we're going to be covering is a lot more of the building blocks and basics of machine learning that are important for deep learning, that are important for AI research. But our goal is to set up this pipeline that hopefully will help in discovery projects, in actual curricular related requirements, as well as trying to encourage the School of Medicine to increase its teaching of machine learning. It's going to become this tool that we all have to understand, both its power as well as its limitations, just as much as we understand EBM, or just as much as we understand how decisions from the literature get translated to patient care. So that's really the core, those are the core goals. So hopefully everyone can see my screen. Avinash, can you double check and voice whether you can see my screen?
Yeah, it's on.
Okay, great. So we're gonna start from scratch. So you had an email sent out a few days ago that has links to several things, but we're gonna focus in on the notebook specifically. So if you go down to this link and click on the notebooks link, it'll take you to a Google Drive-like environment. And you might see something like this. Okay, so this is a great starting point. This is a preview of what the notebook looks like. And this notebook is a living document. It's a document that has text in it, that has figures in it like a textbook or a paper would, but it has a unique feature that it has code built into it. So you can actually code as instructions. And so a notebook, a Python notebook, Python is the language that's used to make the programming code. Those are essentially like instructions. And what Collab, which is Google Colab Collaboratory, however you want to say it. That is an environment that lives in the cloud, some server that Google has that actually goes in and runs these notebooks. They actually run these living documents that then run the code and put the output of the code directly into your notebook. So that's nice in theory, but we're actually going to work with it right now. So if you click the link, right now we're doing screen share just so we're all looking at the same thing, but hopefully we encourage everyone to go play around with these notebooks and get a hands-on understanding of these notebooks. But we'll walk through it right now. So this is the preview. So if you click the link, you'll be on this screen right here. What I just did was I clicked open with, and I clicked Google Collaboratory. And when you click that, it opens that notebook in an interactive environment. That interactive environment is Collab. This is Google's server-based way of running notebooks, running these Python notebooks on some machine somewhere. And why we chose to do Collab is because it lets us do consistent running of notebooks. Notebooks are code, so they need certain properties, they need certain libraries. We'll cover this next week if you're interested in local versions of this. Collab runs on Google servers, but there's a way you can run something that looks like Collab on your own computer, which you might want to do if you're dealing with sensitive patient data. To my understanding, Collab is not HIPAA compliant, and Collab has no relationship with Emory. So everything we're doing with these notebooks is using simulated data. But if you want to run these notebooks on patient data, then you might want to download it and run it on your local machine. But for now, Collab runs these notebooks. And when it runs these notebooks, it runs the code alongside with the text. So let's take a look at an example right here. This is the introduction page that if you click the link from the email and click open with Collab, you'll sort of be in this environment. And there's several resources here, a little bit of text here. This text is primarily for guiding you after the workshop, not during the workshop. We're not going to sit here and read these, but they're meant to help guide you through some of these examples on your own. So what we're going to do today is we're going to focus in on one specific notebook. We have 3 notebooks available, and they're available right now that we're considering core notebooks. These are going to be the core notebooks that really address the foundations of machine learning. And we'll be covering these notebooks again and again over the course of the next 2-3 workshops. But for today, we're going to focus in on basic linear regression. So we're in this notebook. We're going to click the link, and we're going to see what this notebook looks like. This is a separate notebook, and Collab is going to open this notebook. And as we're waiting for it, we'll notice, okay, it looks a lot like the notebook we were just in, but it actually has a lot more code in it. And so you'll notice certain things. You'll notice that there's nice text. It's formatting. There's figures in here, which we'll cover briefly. But before we dive into linear regression and the basics of linear regression, we want to talk about several things that make the notebook relatively unique as a learning environment. So Collab, with the code that is already in these notebooks, enables us to have interactive notebooks. Interactive meaning you can actually adjust different values and see how the machine learning algorithms adapt to it, or how you change a data set and how the machine learning algorithm either fails or does a really good job. That is so crucial to iteratively learning, getting your hands on machine learning experience. So we're going to start with Collab. What is Collab? Collab is this environment that you see here in this screen. It has your main view here, which shows the text. Right now, we're only looking at text, but the code is also shown here. And the figures that are generated by the code are also shown here. The second most important thing in Collab is this menu up here. So you'll see File, Edit, View, Insert, and Runtime. Runtime is probably the most important to discuss today. When we have this notebook, we have text, but we also have code embedded inside this notebook, which means we need to run this code. And that's where runtime comes in. What runtime does is it says to Collab in the server, go ahead and make your way through this notebook and run any code that you see. So if you click runtime and you click run all, this is a good policy. Every time you open a notebook, go ahead and run all. What that does is it tells Collab, go ahead and run all the code you find in this notebook. You might not see anything change in the screen. So right now it's theoretically running through the code in this notebook and making and following the instructions that the code said. But it's important to click runtime, click run all to actually populate to actually make the notebook into the final form that we're going to be able to do, the final draft that we're actually going to be able to go in and learn machine learning in. Okay, so that's an important piece of it. Another important piece of it that we wanted to let everyone know about is this ability to collapse cells. So let's talk about what a cell is. If you see on the screen right now, this right here is a big cell, and a cell pretty much corresponds to a paragraph or a block that lives on its own. And so you'll have one cell up here that's just the title of the notebook. You'll have one block here, which is the license. So these notebooks are open source licensed, meaning our goal is to essentially set up code that you can use as a preliminary jumping off point for any analysis that you want to do. There are plenty of caveats there. The code is going to be very basic. You're going to have to do plenty of work on top of it, but this license says go ahead and use this as a starting point for any analysis you might want to do. And so each of these cells should have the ability to collapse. And when I say collapse, I say press this arrow over here. And what it does is it hides all the code associated with that cell. Just for the sake of example, just to highlight how important this is, I want to show you this code. It's overwhelming. Don't worry about it. What we can do is we can say, you know what? I don't want to pay attention to the code right now. I'm going to collapse this. And so what it does is it collapses it so you don't have to view the code. I would highly encourage, if you get overwhelmed with the code, go ahead and try your best to collapse it. You can always revisit it later, but that code still gets run when you go up to runtime and run all. So that's the beauty of it. You can hide the code so you don't have to see it. It's in the background. But when you run the notebook, you still run the code. And so code setup is one example of a cell that we're not going to spend any time today talking about, but it has a lot of the setup needed to run the rest of the notebook. And what we will do before we dive into the example of Collab, the example of linear regression, is make a real quick comment about code, running code, and specific types of code, which is this slider. This is the interactive component that we were talking about. The goal is to set up these notebooks so that we can actually adjust the values that we're looking at. We can actually adjust the data that we're simulating or the data that we're analyzing in real time without having to code. So you'll notice you'll have these kind of sliders that let you move from the left to the right that adjust the value that is that the rest of the notebook is actually built off of. Two things with this. One, when you make an adjustment to these interactive components, for the most part, things are in the background updating live. But every now and then you're gonna think it's a good idea to just go ahead and run this cell. Before we went to runtime and we did run all. That means run all of the cells. For now, we want to just rerun this cell. So you can go over here to this play button, click play, and it'll rerun just that cell, which gives us the ability to then adjust the setting again, and it resets things with that cell. When we adjust the truth bar here, for example, we might want to go to runtime and click run after. I mentioned this, it's an important piece because the rest of the notebook might depend on this value that we select here. So if you find one of these interactive sliders and it just seems to do nothing, you might want to go here, run that cell again to reset it, adjust the value, and then go to runtime and click run after. And what that does is it runs that cell and everything after. I hope this isn't super overwhelming. The whole point of doing this exercise is to just identify the 4 core steps that you might need to do to get the rest of the examples that we're about to go through running. So that piece of it was very much, how do you run, how do you work with these notebooks? What is Collab? How do we work with Collab? All of that is Collab specific and how to run notebooks. The next step is to dive in a little bit and let's talk a little bit about linear regression. So linear regression is really the core of machine learning. It's the basic building block of machine learning. So spending some time with linear regression, I think, is important as a first workshop. But you'll start seeing that the standard linear regression that maybe all of us have experience with, it's fine if you don't, is really in 2 dimensions. We have an independent variable, some variable that we adjust, and we have a dependent variable, some variable that we're measuring to see if the independent variable changes the dependent variable. So we'll sit with it, we'll focus today on this example, this linear regression example, but keep in mind our goal is to really ramp this up. We're not interested in just two-dimensional regression. We are interested in really high-dimensional regressions. How do 12 different factors contribute to this one variable that I'm interested in? This is just the building block for that. So let's orient ourselves. We're trying to do a linear regression, and we uniquely with these notebooks have the ability to simulate data. We can the goal is to have folks who have data to be able to drop in their data, their patient-specific data, their discovery-related data. But for the sake of today, we've set up code that generates this simulated data so that we can actually apply machine learning to it and see how well the machine learning does in guessing, in educated guessing, what the true value that we put in was. That's the unique strength of simulating the data, adding a little bit of noise or static, and then seeing how well these machine learning algorithms do. We won't spend time today on how the data is simulated, but if you're interested, the code is actually up there in one of the code setup blocks that we collapsed. All of it's kind of transparent and open source in that way. So let's dive in. The example we're going to base this off of is a little bit of an oversimplified example, but hopefully conveys the power of regression. We're going to say that we have the hemoglobin A1C of patients. And let's assume we don't have prior knowledge that the lifetime risk of cardiovascular disease is related to the hemoglobin A1C. Our job is to collect a data set that lets us actually find out the relationship between the two. And what we're doing here is we're actually going to set that the true value. How does hemoglobin relate to lifetime risk? We're going to say that it's 4. So take whatever hemoglobin A1C you measure in the patient, multiply it by 4. That is the lifetime risk of cardiovascular disease. That's going to be the simulated data set that we're going to work with. So we set the truth at 4. We'll go ahead and collapse this so we don't have to really think about how the data is being generated. And now we're going to we're going to do our simulated data set. We're going to do a simulated experiment and see what our data looks like. So if you can look at the code, look at the code. If you are overwhelmed by the code, feel free to ignore the code. What we're going to focus on today is really these figures. And just realize that these figures are generated when we do runtime run all. So this is what our data looks like. On our x-axis is the A1C of our patients. We have about 100 patients in this data set. And on the y-axis, we have lifetime risk of cardiovascular disease. And so these were just measurements that we made in a simulated experiment. We know that the true relationship is 4, but act like we don't know it. We have this data. All this data is the blue data points that we have. And we kind of squint our eyes and blur our vision and say, yeah, I think there might be a relationship between these two. I think there might be this dependence that the lifetime risk of cardiovascular disease seems to be dependent on the A1C. There seems to be this pattern between the two. That's where linear regression comes in. I think there's a pattern here. I assume that pattern is a linear relationship between these two variables. So let's go ahead and make a machine learning model that does a linear regression model. So we have our data, and now we want to actually implement a linear regression model. I will draw attention to the code just briefly here to show how straightforward it has become through a lot of the tools that have been developed to run linear regression models. This is the power of machine learning. This is why we think it's very important for medical students to learn machine learning, because this one line right here sets up a linear regression model and then fits that model to whatever data you have. And here we have an experiment with our A1C, and here we have the same experiment. We have our lifetime risk of cardiovascular disease. That one line sets up a regression model and then runs a fit for that. Then we have other lines of code to assess, to see how well our fit is, and to identify what the estimate is, which we'll get into now, but we'll do it in a graph. So this block of code is really just to display the linear regression in the data that we had. So when we run this cell, let's go ahead and run it as an exercise. What it does is it runs that cell, runs the code in there, and generates your figure. So this is the figure that we see. Our true relationship, the relationship that we set with the slider above, is here in this blue dotted line. That's the truth that we defined that generated our data. This red line is the linear regression that was calculated from just the data. You'll notice it's pretty close to the truth. So that relationship between our A1C and our lifetime risk of cardiovascular disease comes out to about, we set it at 4, and our linear regression recapitulates it. It actually finds out that 3.9 looks like the slope. It looks like the relationship between A1C and lifetime risk of cardiovascular disease. So this is a perfect example, right? We have a lot of variability around that line. It doesn't fall neatly on that line, but the linear regression is able to kind of look through the data and find that commonality that they all seem to share. That is, in a nutshell, linear regression. Here we just did it with 2 variables. The power of machine learning is really doing it in many, many more variables. So what we're going to do next is just highlight the unique ability to do interactive examples with linear regression. So it's the same concept. We're not introducing any new types of regression. And we'll do this pretty quickly before we dive into Alex's portion, which is talking about where machine learning is being applied. So if we look at here, we actually can start exploring the impact of sample size in our ability to do a regression. So let's look at same example. X-axis is A1C, Y-axis is lifetime risk of cardiovascular disease. But in this case, we have no static in our measurements. Our measurements are perfect. They're absolutely perfect in both the A1C and in the lifetime risk of cardiovascular disease. In this case, we have 100 samples, like the example we just did, but we can actually draw those samples down. So let's move down to, let's say, only 6 examples. We only did 6 patients. We collected 6 patients worth of data, and we're trying to fit a line to those 6 patients worth of data. Because there's no noise, it's actually the easiest thing in the world. There's no noise. Each of these points falls exactly on the line that we defined. That's great. This is fantastic. We don't really actually need even 4 data points or 6 data points. We need 2 data points, and we can hit that relationship perfect every time. Great, but not really helpful in the real world. Because in the real world, we have noise. So we can go up here and we can increase our noise. And as we increase our noise, we notice that those dots start going far away from the truth, that true line. That is, by definition, what noise is. It's you measuring something that you care about, and then it being kind of adjusted a little bit because your device isn't perfect, or because the lab had a mistake that day, or something along those lines. That's what noise does. So let's ramp the noise up all the way up to 21, 23. What you should notice is that that orange line, the regression that we're doing, is so unstable and so unreliable that as we're running through different noises, as we increase the noise, that line goes all over the map. And you can do this interactively on your own with these notebooks. Let's find a particularly bad one. This is a pretty bad one, where the true slope is 4, but because we're trying to fit a line to just 2 points that are noisy, the line that the regression finds is way off. We know it's way off because we simulated the data. The solution to this is to increase your sample size. This is the typical power analysis of EBM. How many samples do I need to account for the fact that I have noise in my measurements? So let's do that. Let's do that interactively. Let's start increasing the number of samples we see. And as we increase these numbers of samples, we notice that our regression line in orange really starts matching up with the blue line. It's more reliable. This is why it's important to have large sample sizes if you're dealing with a lot of noise. We will have notebooks where we talk about what do you do if you just can't have more samples. Turns out with machine learning in a frame called small data, it's the opposite of big data, you can actually use other knowledge to come in and help you do the regression, even though you don't have a lot of samples. So this is a great thing. I would encourage everyone to get hands-on with this to see all these different combinations of noise and samples. How many samples do you really need? This is a separate example where we add an extra slider here that shows slope. And slope is an analogy of effect size. So if you're expecting a large effect size, your slope is really high. Noise doesn't matter as much. You can actually do the same, a really good regression with fewer samples and high noise. Don't worry about it. I encourage everyone to get hands-on with these notebooks to actually see what they test your understanding by interacting with the data. And don't be afraid of changing the code if you're so inclined, but also don't be afraid of moving these sliders anywhere you want. There's no damage you can do with this notebook. We have backups, we've saved it all. So even if you can edit them, don't worry about it. Go really explore this space. Okay, so just to end on this, I wanna bring it back to the ground. We just did a simple, kind of a relatively straightforward two-dimensional regression. What we can start doing, and we'll start doing this with the next workshop, is we can start increasing the dimensions. We can start looking how two variables relate to the one variable we care about. That's the example we have here, where you can actually do two variables, two independent variables. You have X, you have W, and you have Y on the Y-axis. And you can start doing these regressions in higher dimensions. You can start noticing if there's patterns in these higher dimensions. And this is an interactive 3D plot, so you can actually go in and you can look around in this yourself. What we've noticed is there is no regression done on this. This is the exercise that we'll do in the next workshop. But it might be difficult to find a pattern in one view. If we just look at this view, it doesn't really look like there's really any pattern. But if we look at all the views, we can actually start seeing, wait a minute, it looks like there's a distinct plane. It looks like there's a very specific pattern between X, W, and Y. That starts scratching the tip of the iceberg of what the power of machine learning actually is. So just to end it and bring it back to Avinash's example, what we did in this notebook was get familiar with Colab a little bit, hopefully enough to run these notebooks. Feel free to run them. Don't be afraid to run them. And don't be afraid to see the errors or make the mistakes. Just kind of work through it. And then we went through a specific example of a simple two-dimensional linear regression. What we did was what's on the left over here. In Avinash's example, we looked at several lab values and tried to see how it related to whether a patient was doing well or not. What we did in this notebook was we focused in only on one variable. We focused in on A1C and how it relates to lifetime risk of cardiovascular disease. But in Avinash's example, it would be as if we did a sodium and just focus on sodium and see how well we could predict how healthy the patient was from just their sodium. That's not what you and I did when he showed that example. What we did was on the right side, we looked at several variables. I think there's probably 6, 7, 8, 9, 10, 11. There's 11 variables there. We looked at all 11 variables and we saw how they mapped to whether the patient was well or not. And importantly, we didn't just look at each one in isolation. We looked at their interactions. We're trained as medical students to look at interactions. I'm going to look at the sodium, sure, but I'm also going to look at the potassium. I'm also going to look at the glucose because I know that they're all related. And so when I look at those three variables together to then make a decision, do I expect this patient to have diabetes or are they in DKA? Then I'm actually looking at multivariable regression, multidimensional regression. This is the exciting part of machine learning. Not only is it exciting, we have a notebook set up that does this. We won't talk about it today, but the goal is to actually look at more variables than we can visualize and actually identify patterns in those high dimensional data sets, much more than 11. We can look at dimensions of 100 different variables and how they map onto whether a patient's doing well or not. And in this example, if you click here, you'll notice that we go to an advanced linear regression example. We do this, but we do it in the coagulation cascade. We are not going to spend any time on this. This is kind of just a preview of what the next workshop is going to be. But in a coagulation cascade, we've got so many different variables going. Our job is to use high dimensional linear regression to figure out what's happening in that coagulation cascade. All right. So with that, we've got a little bit of an introduction to linear regression and how it's the building block of much more advanced machine learning. What we want to end on is where's machine learning helping with medicine today? And what are the exciting frontiers of machine learning that we should, as medical students, be prepared to plug into because those frontiers are really, really where advancing patient care really are. And for that, Alex is going to take it over.
All right. Hello, everyone. I'm going to be talking about machine learning application as it pertains to healthcare, and I'm going to go over some examples that are going on in society as well. And to start things off, I wanted to show you guys this slide. And it basically this graph is years until a certain technology is used by about 25% of the population. And you can see on the left around like 1967-ish, electricity. And it took about 46 years for a quarter of the population to use this technology. Then you see telephones, 35 years, and so forth, and it keeps going lower and lower. And then on this other end, you can see smartphones and AI. It only took 2 years for about 25% of the US population to adopt. So basically just kind of setting things off that this technology is growing and it's pretty rapid. And then I want to highlight some AI and ML applications in healthcare, and then also show you guys that some are happening at Emory. And as you can see from the title, this is a machine learning approach to predicting psychosis using semantic density and latent content analysis. And from our psychiatric modules and rotations, we learned that the onset of schizophrenia and other psychiatric disorders typically occur around the early 20s with warning signs known as prodromal syndrome. And this usually happens around 17, 18 range. And about 25 to 30% of the youth who meet criteria for this will actually develop full-blown schizophrenia or another psychiatric disorder, or a psychotic disorder, excuse me. And so the researchers of this wanted to know, like, how can we predict or find individuals going down this path? And maybe they thought language or the way we speak was a way to do that. So what they did was pretty amazing. They identified language norms in everyday conversations by feeding their software into Reddit. So looking into 30,000 Reddit users conversations, they found out what semantic densities were of conversations that were norm. So they found out what normal was through this model. And then they tested their model on diagnostic interviews of young people at clinical high risk for psychosis. And they compared it longitudinally to who of those individuals actually developed it. And the results showed that higher than normal usage of words related to sound, I literally mean words like describing sounds, combined with a higher rate of using words with similar meaning, meant that psychosis was more likely to happen. So now to highlight another example going on at Emory, it's a company called Vitals. It's a startup in Atlanta and I believe in New York. And what Vitals does is it makes EDs more efficient by triaging patients faster. And Vitals basically predicts a patient's probability of admission based on a bunch of parameters: age, chief complaint, lab results, etc. And basically, they try to focus on which patients need help now, opposed to maybe we can see this patient later, and predict admission rates, so to streamline EDs to make them faster. And now next, I want to highlight just a kind of a case of deterioration. And by deterioration, I mean coding. So we're going to go over this example. So hopefully you can see my mouse. I want you guys all to just think about like heart rate right now. And so say your heart rate is around 60 beats per minute. And say you go to sleep, it goes to 50 beats per minute. Then, you wake up, it's back to 60. Say you go on a jog, it goes up. What I'm trying to say is that that's stable and subclinical variation, and that's normal. So then say you're in the hospital, you're not doing too well. Before you code, there's actually a point called subclinical deterioration. And so there you go down this path and then you end up coding. And the way our hospital system's set up right now is that we treat you when the code happens. So for example, in 1953, ICUs were created. 1960, CPR was invented. 1979, advanced CPR was invented. And then as you can see on this graph on the left, mortality rates are not great. So like in hospital cardiac arrest, 75% mortality, sepsis, 15% mortality, respiratory failure, 40% mortality. So we're really not necessarily that great at treating codes. So now looking at the same arrow, I want to highlight this area. And this is really where the money of AI and ML is. Because if we can feed data into a algorithm, we can predict if you're going to code or not, and then hopefully save lives. So right now, this is the norm at most hospitals. It's called the Modified Early Warning System. It's called the MUSE, and it predicts your ICU admission or death within 60 days. If you just plug in from systolic, heart rate, respiratory rate, temperature, etc., it'll give you a percentage. And this is actually my percentage. So this tells me I'm going to die or be in the ICU by 8%, which is pretty insane. I know a lot of you guys are out there would have the same thing. So this is the current model. So I hope it's wrong. And so this is its prediction. So this is an area under the curve. So think of it, it's like a p-value where closer to 1 is a perfect prediction, that's excellent, and 0.5 is not good at all. That's like a 50, that's a coin flip. So this model is a 0.58, so it's kind of a coin flip. And so now I want to highlight a hospital system that actually used an ML AI application to start predicting that subclinical deterioration area. So they used Epic, and they found, so they got all patients' data into Epic and basically made an algorithm using to predict if the patient was going to code or not. And so their model had a 0.89 prediction using their AI and ML. And it didn't give you a 60-day prediction, it gave you a 4-hour prediction. So what they would do is they would say you're a hospitalist on, on the rounds, you would get some alert saying, hey, your patient's not doing too well. You need to go check in on them now. And they would go in there and assess the patient and see what was going on. And what this did was it successfully reduced codes outside of the ICU by 44%, which is amazing. Over 40% of alerts result in transfer to the ICU. Over 25% of alerts result in end-of-life conversations, which is very important. And this was just a 90-day trial. And once again, it was a 0.89 area under the curve, so a very high value, and 1 being perfect. The next example I want to highlight is diabetic retinopathy. So I know, so human error rate across the nation is around 20 to 30 for diagnosing this. I know Emory has an amazing technology program, and I'm sure it's much lower here, but you can also see that the AI error rate is less than 13%. And so, yeah, like I was saying, the AI model is less than 13%. And the FDA agrees that, as you can see here, it approved an AI device to detect diabetic eye disease without a clinician's involvement. So this is the first time basically in human history where artificial intelligence or a machine is capable of making an independent diagnosis without human supervision, which is pretty remarkable. And now I want to highlight some examples of AI and ML in society and just in life. So this was a Google study. And during this, you might have seen, around Atlanta or wherever, that those Google cars, and they have cameras on top. Some of them I'm not sure if it was in Atlanta or anything, but they were just taking pictures of cars, and they were trying to predict this stuff: census estimation, voting trends, regional income, etc., just from your car, just from the picture of your car. And so this right here is their predicted of income in Boston on the right, and this is their actual on the left. It's pretty insane. And I was looking at the audience. I know some of you guys Boston, but I forgot which was the dark red or the yellow was rich and which one was poor. But maybe you can tell me if this is true. This right here is voting patterns in Phoenix. It's predicted on the right, actual on the left, which is pretty. I still can't get my mind around it because it's not like all liberals drive hybrids or anything, So I mean, it's insane what this algorithm, can do. But this also brings up the question of ethics. And ML is very good at predicting things based on patterns, but correlation is not necessarily causation. So we just always have to keep that in mind. And then I want to finish this presentation just on the final slide of, this was voted by healthcare execs, rating AI and ML as the most disruptive technology in healthcare. And as you can see, it's substantially higher than drones, but it seriously is like, it's showing you that healthcare execs are very interested in this market. And then this is the health AI market size from 2014 to 2021. 2014, 600 million. And then in 2021, it went to 6.6 billion. And actually, Avinash and I just started our MBA on Monday. And it really doesn't take an MBA to realize that an 11-fold increase over 7 years is insane. And this final slide is basically just to highlight that, AI and healthcare is, on the horizon. And these are just some exciting examples of what's been happening. So with that, I think I'll send it back over to Vineet for questions.
Thank you so much, Alex. Thanks, Avinash. So thank you all for listening. We, I think, are very excited about the potential that the workshop can have. Hopefully this gave you an idea and an introduction that we're going to build off of in subsequent workshops. One thing I will say is the workshops, you know, we started talking about this in January, February. A few things have happened since then. And being in person and working through the notebooks in, for example, the School of Medicine computer lab is the vision for workshops. So we're going to be as adaptive as possible and try to shift things over to Zoom in the meantime. But I do want to stress this workshop is a longer term initiative that is focused on getting hands-on experience with machine learning in the context of the future and what's currently happening with machine learning, as Alex covered, as well as a foundational understanding of what machine learning is built off of, as Avinash covered. And the notebooks are really meant to tie together the workshops, the kind of more talking about algorithms with the action part of it, which is the working with the algorithms, the exploring different parameters and seeing what the machine does with the sliders and the interactive component of it. So that's a little bit of context of the workshop as a whole. I don't know if Avinash and Alex have any other comments before we open it up to comments and questions.